Hello everyone, my name is Donghui, and I'm a PhD student from the Hong Kong Polytechnic University. I'm very excited today to be here to give a introduction about our work, RFID+, spatially controllable identification of ultra-high frequency RFIDs with controlled magnetic fields. In this work, we use the magnetic field to read RFID tags selectively. This work is collaborated with Zhenlin, Zheng, Gong, Qingrui, and my supervisor, Dr. Ray Yang. This project is motivated by the trend that spatially controllable RFID inventory has many applications. For example, in a warehouse setting, our focus lies on efficiently managing inventory. Only tags stored on specific shelves need to be checked and inventoried. Similarly, within a retail scenario, our attention is to enhance the checkout process for customers. Only products in a customer's shopping basket need to be recorded and checked out. Other items should not be detected by the reader. Furthermore, in a manufacturing factory, as products has been placed on conveyors for transportation, the readers would only want to selectively check the tags within each box at a time to make sure the number of items is correct. However, current UHF RFID systems face two anomalies when trying to achieve spatially controllable reading goals. The first one is called the misreading anomaly. It means that the wanted tags cannot be fully detected. Some tags are missing. And second anomaly is cross-reading. And it means some unwanted tags has been mistakenly detected. For example, a customer may sometimes find that some unwanted products from nearby customers also been detected by the auto checkout system. Both the misreading and cross-reading are unwanted phenomena for UHF RFID systems. The reason behind these two anomalies comes from the propagation behavior of the UHF RF signal. As shown in this figure, when a UHF RF signal is propagating with distance, multi-path signal will sometimes be disjunctively combined together within the region of interest. The signal strength in such locations will become lower than the tag sensitivity, and hence it will cause the misreading problem. Similarly, the multi-path signal will also be conjunctively combined outside the region of interest to cause the cross-reading problems. Therefore, how can we address misreading and cross-reading problem at the same time? Our insight is to use a magnetically driven UHF RFID system to overcome these two challenges simultaneously. This red line shows the propagation of magnetic fields, and we found that the magnetic fields have two remarkable advantages. The first one is high penetrability. It means that the signal will monotonically decrease and no disjunctively combined signal will generate within region of interest. And the second one is rapid attenuation, and it means that the signal outside the region of interest will also not be conjunctively combined. Based on these advantages, it's possible to utilize a magnetic field empowering the inventory process of UHF RFID? The answer should be yes. We found that every RFID tag inherently incorporates a singleton coil called matching loop, as shown in these two figures. Such loops can naturally act as a receiver antenna for inductive coupling. Specifically, as shown in this figure, the magnetic induction line can travel from the reader's loop antenna to a tag's matching loop. Such a coupling can capture magnetic energy from the reader and then power the tag for communication. To verify the feasibility of inductive coupling by using matching loops, we first conduct a preliminary experiment as shown in this figure. We use a coil and patch antenna as transmitter, respectively, as shown in this figure. Then we cut off RFID tag's dipole antenna and only retain the matching loop for energy harvesting. A USRP device is used as a receiver to sniff the communication process. And we have the following two findings. The first one is no signal can be detected when the TX is a traditional patch antenna after the tag's dipole antenna has been cut off. However, we do observe a normal reply signal from text if we change the TX antenna to a coil antenna. This result validates that the existing RFID text can be activated and queried using a magnetic field, while the communication protocols can remain unchanged. Therefore, we propose our work called RFID+. It is the first spatially controllable magnetically-driven UHF RFID inventory system, and we introduce techniques like innovative coil antenna design and faster inventory algorithm. And our systems can achieve a 99% discovery rate and nearly zero cross-reading rate within the region of interest. But designing such a magnetic-driven RFID systems into practice face many technical challenges. The first one is how to generate a uniformly distributed magnetic fields at the UHF band. This challenge comes from the fact that many bright zones will exist at the UHF band if we use a simple loop antenna directory. To better visualize the problem, we use a software to simulate the magnetic intensity distribution at HF and UHF band respectively. This figure shows the simulation result at the HF band, where the signal frequency is 13.56 MHz. We found that the current around the loop can remain almost in phase and of the same size because the wavelength is greatly larger than the coil perimeter. Hence, it can produce a uniform magnetic field. However, the result will be quite different in the UHF band. As shown in the right-hand side figure, we found that the current around the loop cannot remain in phase again because the wavelength is almost compatible with the coil perimeter. Therefore, many bright zones will exist, and a uniform magnetic field cannot be generated in this case. Our solution for this challenge is to use a capacitor-segmented coil antenna. Left-hand side figure shows the structure of a traditional coil antenna, and the right-hand side figure shows the capacitor-segmented antenna. By segmenting the loop physically and inserting capacitors between adjacent segments, each segment can be modeled as an equivalent RLC circuit. The inserted capacitor can compensate for the phase shift caused by each segment, and hence guarantee that the RF signal remain a uniform initial phase shift across segments. No out-of-phase magnetic field will be generated. Similarly, the simulated result demonstrates that the capacitor-segmented coil can maintain the loop's small size while guaranteeing a uniform magnetic field distribution. Besides the capacitor-segmented coil, multi-turn coil can also spread the magnetic energy more uniformly, as shown in these figures. After simulation, we found that a 4-turn design can achieve a balance between the maximum magnetic intensity and minimizing the mutual coupling among coils. Therefore, we finally used the 4-turn capacitor-segmented antenna as our design. Next, the second challenge for our system is how to precisely manipulate the magnetic field to achieve spatially controllable reading. To precisely control the magnetic field, the first thing we need to do is to direct the energy in a single target direction. Why we have to do that? This figure shows a coil antenna and the bidirectional magnetic distribution characteristics along the z-axis. However, in most application scenarios, the bidirectional property is unwanted because it will waste half of the energy outside the region of interest. The question becomes how to confine the bidirectional magnetic field distributed in one direction only. Our solution is to use a mushroom-like high-impedance surface as a reflector to constructively reflect the backside energy to the front side. The structure of the HIS reflector is similar to metasurface, which is formed by many element cells. The side view of an element looks like this, and each element can be modeled as a parallel LC circuit. Therefore, the impedance related to an HIS reflector can be expressed as follows, which is the same as the classical LC circuit. The magnetic field's reflective phase by the HIS reflector can be further modeled as theta. We can see that when the incident field oscillates at resonant frequency, it means that omega equals to omega hat. Therefore, the impedance will be approaching to positive infinity, and theta will close to the 0. Consequently, the reflected magnetic field will have 0 phase shift, and therefore it can be constructively combined with the forward propagating field. As shown in the simulation result, we can see that the HIS reflector can successfully reflect the magnetic energy in a single direction to enhance the spatial controllability. In addition, we also use a coil array to enhance our system's spatial controllability in 5 gram further. This figure shows the principle of magnetic beamforming, and to achieve this, we custom designed the near-field reader by using phase shifter to adjust the focal point's location. And for more detail, please refer to our paper. Okay, next I will introduce the final challenge for our system is how to quickly detect all text in a brief time frame to ensure a smooth customer experience. Currently, faster inventory is a desirable yet unachievable goal because of the following 3 reasons. First is called short response time. RFID systems has only several seconds to take actions before text has been moving out of the region of interest since the size is small, as shown in these 2 figures. And second is high throughput. About 100 to 200 texts need to be detected at each time. And third is called maxi correction. For an RFID systems, nearly 74% of the time is lost to channel contention. These 3 challenges make it faster inventory cannot be achieved in current systems. To solve this challenge, we propose a dual coupling inventory strategy to combine both radiatively and magnetically driven RFID systems together to enhance the reading speed within region of interest. Specifically, in phase 1, the far-field reader will identify a set of candidate texts in advance by using electrical field. The corrected EPC are then used to construct a Bloom filter. Next, in phase 2, the near-field reader will use the previously obtained Bloom filter to check for the presence of text within the region of interest quickly. After simulation, we found that the communication overhead can be reduced by about 60% by using Bloom filter to speed up the inventory process. Yeah, so far I have introduced the theoretical analysis of our system. Now I will introduce the implementation and evaluation. In this work, we use USRP X310 software-defined radio as the reader, and Raspberry Pi and phase shifter are being utilized as a beamformer. Last but not least, we also custom design a 2x2 coil antenna array and HIS reflectors to act as the transmitter to generate the magnetic fields. And we first text systems inventory accuracy. In the text, a dense collection of 100 texts was fixed to a flat surface. The accuracy was measured based on the discovery rate. This figure shows that RFID Plus excels in detecting text within region of interest up to 175 centimeters with a discovery rate larger than 95%. And the performance significantly decreased beyond this range. We then focus on system spatial controllability. We direct the beamforming focus to 5 positions along the z-axis. For each position, the text backscatter signal strength was measured. The results are shown in this figure, and the conclusion is that the beamforming focal point increased the average receive signal strength by about 7.73 dB at those locations. Finally, we compare the proposed dual coupling faster inventory algorithm against the conventional Q-adaptive inventory method. And we found that our faster inventory algorithm can achieve inventory in just 2.4 seconds, saving 36.8% of the time compared to the traditional algorithm. In addition, we also test our system in a real logistic network, including a textile factory warehouse and a conveyor scanning gateway in Hubei province, China. The evaluation result shows that our system achieved about 1.95% misreading rate and nearly a 0.1% cross-reading rate within a reasonable time slot. Finally, I will give a conclusion of our work. We first demonstrate that a magnetic-driven UHF RFID systems is feasible and valuable. And we first integrate display elements like capacitor-segmented loops, multi-turn coils, HIS, coil arrays into a unified practical RFID inventory system. And our system achieved a 1.95% misreading rate and nearly 0.1% cross-reading rate in our pilot study. All right, this is the end of my speech today. Thank you very much for being here. I'm happy to answer your questions.